So the first section will be the injection molding. So this is the injection molding. So we will put a plastic pad into the hub. And then we will have a screw by rotation, so we can generate the shear stress. So through the shear heating, we can turn this solid pad into melt. And this melt will go through the tunnel to here. So here we can have a melt chamber. We accumulate liquid melt in front of the screw. So, and then we can move forward the screw to push the melt going through this mold. Go through the runner, we call this is a runner, to distribute the plastic melt into the cavity. So we inject the melt into the cavity and then cool down. For example, like a 20 seconds. And then we are able to open the mold, eject the plastic part. So this is a one shot. And then we can do it again to have another shot. So injection molding is a sequential molding. So we produce a shot, find another one, another shot. So again, this is the basic idea for the injection molding machine. So we can put plastic pad into here and drop down through the rotation, generate shear stress. And since polymer is a very high viscous material, so the high shear stress will generate a lot of heat. So through this heat, and also we have a heating element inside the barrel. So we can provide a lot of energy to turn this solid into melt. And then go into the cavity through the runner. Okay. So if we are take a closer look about the molding cycle, actually injection molding can be divided into 3 or 4 stages. Okay. So the first one, we close to mold. Okay. We close the mold. And then the injection unit move forward. So this can push the melt into the cavity. And for this stage, we call this is a feeding stage. So you can think about the melt move forward. And it will advance every after a small time, it advances a little bit forward and continuously fill the mold. So this stage is called feeding stage. And then, since we provide cooling effect in order to cool down the hot melt, in order to take out the part, right? So we will cool down. Through the cooling, since material will shrink if the temperature drops, so we need to provide high packing pressure at the entrance in order to compensate the shrinkage. Right? So this is the second stage. We will provide a high packing pressure to compensate the shrinkage. And after that, the injection unit rotate backward to prepare melt for the next shot. And for the cavity part, it continues to cool down to cold enough, high mechanical strength, allow you able to open the mold. So this cooling stage is the major period for the mold. Typically, we may have a 1 second for feeding, like 5 seconds for packing, compensate the we may have a 15 seconds for the cooling stage. Okay? And there are some factors that affect injection molding. For the first one, we need to design the product. What is the product look like? And how about the thickness? And what is the geometry? And then we need to think about the mold. How to distribute the melt through the nozzle into the cavity. So how to design it? And how about the cooling channel? How to design? How many channels are you going to have for this mold? And then you need to decide which material you are going to use, like ABS or polypropylene, PP or PE, something like that. And then you need to decide machine and process condition. For example, the melt temperature, mold temperature, injection speed, and packing pressure profile. So those are 4 factors you need to consider for the injection molding. And for this injection molding, sometimes we can have some problem. So those are some common defects. The first one is show shot. You want to have a completely filled mold, but sometimes you cannot, since this is very thin. And once the melt goes into this region, it cools down, and it's very difficult to move forward like a frozen. So you cannot have a complete shot. So this is show shot. And sometimes you push too fast. You compress the air, so you can have a burning effect. And sometimes you have a two melt meeting together. So this is a wild line effect. So the appearance is not good, and also the mechanical property. Since the two melt meet together, the molecular chain is not able to penetrate each other very well. So the mechanical property is not good for the well line. Okay? And sometimes you can have a warpage. The size or the shape is changed. So you may have a warpage. Okay? And for the product design, and as I mentioned earlier, so we need to decide the thickness and the geometry shape. And sometimes you may need, for example, a metal insert and inside the mold, and then you inject the polymer and mold it together. This is called multi-component molding. So for the simulation, it needs a fluid and mechanical interference each other, like a fluid and solid interaction. And for the mold design, we can have a several gate design. You can have a flame gate in order to help the melt distribute uniform. And sometimes you may want to keep the surface very good, so you would like to design a gate through the inner part, not outer part. So you can have a several kind of design. And for a very big part, maybe you can have a 4 or 6 multiple gates. So you also need to design how many gates you are going to use and where to locate your gate. And also, this is also why we may use software to simulate, to help you identify those issues. And you can have more than one cooling channel, for example, like 10 cooling channels. How to design your channel to remove the heat efficiently inside the mold. Okay, so any questions so far? So those a few slides I would like to help you understand what is the injection molding and some factor or issue you need to consider if you are going to handle injection molding. So any question? So if not, we are moving forward to see what is the powder injection molding. Okay. So actually the powder injection molding technology was first introduced in 1973 by NASA. Okay. So it combined injection molding and with powder and powder. Okay. So we can have a powder. I believe you are already familiar with the powder type. And then we add some polymer as a binder. And then we mix together and through the injection molding to produce the powder. And the powder can have, maybe you can have metal powder, and maybe you can have ceramic powder. Okay. And then we can distinguish into several stages. Okay. So again, we can have binder, and this is powder. And we want to mix it. So here, pay attention. We try to mix it very well to have a homogeneous feedstock. So we hope this mixing is perfect and very well. This is the first issue you may have. And after the perfect mixing, you can have a homogeneous feedstock. And then we want to make it into several tiny or small patterns. And through that, you are able to put those patterns into the injection molding. Okay? And then we can turn this into floatable mixture. And then we are able to push the screw forward and into the gauge to the top. And once we take out this part, we call this is wing part. Okay. So here now we still have binder and powder inside this. And then we are going to do the third procedure. Try to remove polymer powder. Okay, so this is wing part. If we are able to remove the binder, we can have a ground part. This one is like almost 99% or more. Most of the part are from powder. We try to remove the binder, but somehow we still keep some small amount of powder in order to keep the shape. Okay, so we can have a one part. And then we can just apply extremely high heat to sinter the part. Okay, so after that we can have a sinter part. Okay. And if necessary, you can apply some post-treatment to modify it. Okay, so any question? So this is the powder injection molding process. And then we can take a look about the binding state. Okay, so again, for the green part, we just take out from the injection mold. We still have a lot of binder, which was shown in black. Okay. And then we try to remove the binder. So initially we remove a little bit, and then we keep going remove most of the fiber. And this is the final. So after that, we can say this is a bond part. Okay, any question for the dividing? Okay, if no, then we can take a look about the sintering. So those are, for example, metal powder. So most of the binder was removed. So we can have a gap, some gap in between the powder. And then we apply heat a little bit below the melting temperature. So if the temperature is high enough, so the material is able to diffuse or move. The mobility is going higher, so it is able to like diffuse and mix it together. Okay, and once we finish this stage, we can have a sinter cup like this one. Okay, any question? So for the powder injection molding is applied for manufacturing for the small and complex shape. For example, those are made through the powder injection molding. The geometry is very complicated. So you design a mold help you to achieve that. And typically we always use this for small one, not for big one. Okay, so then we can take a look at how to do the modeling and simulation for that. I'm not sure, are you familiar with those equations? No? Okay. But some ideas, right? You need to calculate, right? Like a balance, force balance, right? If you move this object forward, and if it doesn't move, somehow it has some friction to compensate, right? So we always do the conservation. So the first one is conservation of mass, the density change, and the volume change, the balance between them. Okay. So the first one is mass conservation, and the second one is like momentum, the force balance, the velocity. U is the velocity. The balance between the gravity, external force, and the like F equals ma, right? Mass times acceleration, right? So the force balance. Okay, and this one is T, the energy or the temperature. So the energy, the heat energy may be diffused out, or you generate some shear stress to apply shear heating into this system. So some kind of thermal energy balance. So those are the equations we may have. And then we need to design the very important model. This is constitutive model. For example, we are going to do the mold feeding simulation, so we can assume it's a melt. Not maybe okay. Oh, yeah. Oh. Oh. Okay. maybe I use this slide. So for the powder is like a solid, right? So for the solid, those are the properties you may have, right? If you apply elongation or the normal stress, you can measure the Young's modulus. And if you apply the shear stress, you can measure the shear modulus. And if you compress the powder or compress the solid material, the volume will change. So you can know the bulk modulus. So if you, sorry, this one. This one? Okay. So for the solid, the stress, for example, stress, or maybe use this one. The stress always equal to a modulus times strength. Right? So that's the if you treat this material as a solid, you can have those properties. And this is the model, we call this constitutive model. The strength times modulus into a stress. And this stress, you can have a balance. So this is the idea. But sometimes we can need to assume this is a liquid. Or like a melt. And for this one, for liquid, it will depend on, here is the rate. This is the strength. Strength like displacement, right? Like a delta L. Displacement. And this is the like a velocity. Like a velocity. So we call this rate. And if you are going to treat this as a liquid, you need to decide for the elongation stress, we can measure the viscosity, elongation of viscosity. And for the shear stress, you can measure the shear viscosity. And for the volume change, sometimes you have a resistance, we call this bulk viscosity. And this is modulus times strength. Viscosity times strength. Some model. Okay, so any question for this one? I want to remind you, so you will need some important material property to help you input into this system and help you to simulate the result. Okay, any questions so far? And then we have two more important properties. So this one is the PVT diagram, the specific volume and temperature. Since we are producing the injection molding or the powder injection molding through the high temperature, for example 200 degrees Celsius, the volume here, high temperature, high volume, right? Volume here is very big. And if we use the pressure to compress and then cool down and inject the part, so the volume always change. So the PVT diagram is also very important for us to input to the software. And through this diagram, we can know the alpha, the volumetric thermal expansion, the slope. For example, if the temperature increases 10 degrees Celsius, how much volume will change? So this is volumetric CT. coefficient of thermal expansion. And here, if we increase the pressure, so the model will shrink, we compress. So this effect, we call this is compressibility. I believe like for powder, you also can measure some compressibility. Okay, so those are the ideas. And actually, for Model 3D, we are not just a software company. We also investigate or invest a lot of measurement machine to help us or help you to measure the shear viscosity, PVT, conductivity, or crystallization, something like that. Okay. Okay, so by those material testing method, we are able to let you know what is the viscosity. If we increase the temperature, the viscosity, the resistance to the flow is reduced. And sometimes polymer is very interesting. If you apply higher shear rate, the shear rate is the difference between the velocity. If you increase the shear rate, the flow resistance will drop. So those are key material properties. You need those properties in order to have a success or correct simulation. And this is PVT, thermal conductivity, and heat capacity. Okay, any questions? So once you have those key, you know some idea about the equation, then you also know it's very important to measure the material property in order to put in or input into the software, and then you are able to do the simulation. Okay, and the idea or the workflow will be like this. The software allows you to import a geometry. For example, this is a very complicated automotive part. And then you input into the software, and software will help you to generate the mesh, like some control body, small mesh. And then you need to provide necessary information, for example, the material property. Actually, you can select from the material bank. And also you need to design the melt temperature, process condition like melt temperature, mold temperature, velocity profile, packing pressure profile, something like that. And then you can run the simulation, and you can have a result. Okay, so any questions so far? Okay, so am I speaking too fast? Any question? So, please.
So, based on your simulation that you put your properties, right? Method properties, and this one is based on your testing, right? So then testing only one. Based on your simulation and on the case study, what is how the difference between the simulation you get and the real simulation? What's the result between the experimental and the simulation? And also, how much
sometimes, so for example, our customer maybe will run this procedure and will not measure the material. And sometimes it can have a very good result, sometimes not. Yeah. And sometimes he also paid a lot of money to measure the material in order to have a perfect result, but sometimes the result is not as good as he imagined. So since the real world is very complicated, so there are some factors combined together, right? So like a material property and like a numerical or the solver. Sometimes you are doing the numerical, sometimes you also have some error. Maybe the error is like 20%. So if you do this perfect, like only 5%. But in total, you still have the 20% error. And yeah. So material solver and then people, the user. We have a lot of the functionality now. Some will try the A function plus B. Some will say, oh, it's better for B and plus C. Yeah. So the user, so simulation is like a tool, like a gun, right? Some good shooter is very good. Even the first shot is missing, like he knows exactly how to shoot. So the user is also very important. So, and this is science. Sometimes we are not sure. Currently, we are doing our best. Like maybe 2 years later, we realize, oh, this is not good enough. We have a better method to measure that. Sometimes we also have some issues. So, I should say it's interesting. Yeah. So the experience is also very important. For example, if you graduate and you work like 5 years, and you can be a very experienced, well-experienced user. Yeah. So you will know something about this and this and this, and know how to do the program. That's why we have this lesson and class. Thank you. Any more? Or any other question to the other? Okay. So right now we are going to have a case study about the powder injection molding part. Okay. So before that, we need to review again, right? So what is the powder injection molding? Okay. Some key factors. Okay. Fiber combined with the metal powder, and we can put this pellets into injection molding, have a twin part, and then divide it, remove the binder, and have one part, and use thermal energy to help you sink the one part into a final metal part. So that's the process. But sometimes we would like to have a homogeneous feedstock, but through the injection molding, due to the velocity is very fast, all the geometry design, sometimes the face will separate, face separation. See? So from the SEM micrograph, we can observe some black lines. Those are powder, and these are some areas right now. And sometimes we may have some void or crack. So we believe, all from the academic research, people say this is powder binder phase separation. This was caused by that. And this phase separation between powder and binder is very important enough for the quality issue of the green powder. So see, the wall is no slip. The velocity is 0 at the wall. And the velocity is higher. So this is the thickness. Right? This is wall. Right? So velocity is 0 for 2 wall. And velocity is higher. Higher in the middle and 0 near the wall. So this is the velocity. If this is the thickness direction, right? Velocity is function of thickness. And we would like to know the slope. The slope along this direction. So this is the slope. See, the slope is very high near this region. And this is like a 0 slope and high. So this is the slope. We call this is the shear wave. Okay? The slope of velocity profile. So this is the shear wave. So shear wave is very high near the wall. So high velocity difference will separate the powder, and low velocity difference, the powder will accumulate together. So high shear wave particle will disperse. So we can have a low powder concentration near here. And particle may be concentrated highly in the central area due to the low shear wave. Actually, from this experiment, we can see, right, the concentration is a little bit lower near the wall and highly concentrated. And from the experiment, we can have a result like that. And this is the thickness, 2 wall, the top wall, the lower wall, and this is the center. For the center, we can have a higher concentration. Okay? So any question for this one? Okay, so this is the idea, and we can see how software help you to identify those problems help you to design this. So this is our case. See, so this is a small, not big part. It's a small part, but actually very complicated. This is a real case for the metal injection molding. And we would like to use the software to help you identify the black line and know the warpage problem. And for the software, we can provide user the melt form, dwell line, position, concentration, result, and where is the black line, and how big is the warpage. Okay. See, so if you know how to use the software, so you are able to have a result like this. So the melt will go into the runner and into the cavity. And for this complicated part, a 3D melt form can help you know how the melt is advanced inside the part. And see, this is a well line, two melt meeting together in this region. And for the feeding time, as I mentioned, we will have a feeding stage, packing stage. For the feeding time is very short, like 0.284 seconds, very short feeding time. And then you can have your report. Like a feeding volume percentage, 15% look like this, and 50%, 85, 94%. So you can use the software to generate the report. And software can also do the particle tracing. So like every time step or you can identify, you can decide how many particles and how many times you need to put or trace the particle. So the first you input is the red one, so you can know how long and how does this particle go into this region. Okay. And then you can identify the well line, the two melt meeting together. See? So this is the meeting line. So any question for this? Okay? And then we can provide the concentration result. So how the concentration weight percentage 60% or 58.4%. So there's some distribution. You can know which area is higher, which area is lower. And this is the see from this. So this is the center part. This is the one part. And this the black you can see it from your eye. Right? This is the black line. The concentration is not uniform. And for the simulation software, you can identify this concentration is quite different from this one. So there is some edge. And we can see from the concentration result, those lines are identical to the experiment. And not just for the one part, if if you sinter to have the final part, those areas may have a poor property. Okay? Any question? And since you are going to have a mode to help you to do this part, and there are some heat may be accumulated inside those cavities. Right? It's difficult to remove heat from this one. So the heat accumulation inside the mold is very important. So we also provide a result, or this is mold temperature difference between the. We will have an upper half and lower half, two half mold, and close together, right? The temperature difference between this half and the other half, we call this mold temperature difference. And this result show you the difference is higher than 10 degrees Celsius. So these are the hot spots. And then this part is going to shrink inside the mold or open the mold. It continues to shrink due to the temperature reduce. So software can help you visualize how the geometry is changing. And see this region has some wattage issue. And from the experiment, we can also see, if we put this part on the table, you can see some shade, right? So, which means it's deformed upward. Right? So this is similar. Or we can show have a very good agreement with the experiment. Okay? So for this case, here's the summary. So the software can help you know how the melt advances, right? And show you the well line. And maybe some air will trap for those regions. And we also provide powder concentration to help you identify the black line. And more temperature difference can help you know where there is a heat accumulation. And if you want, you can try to do a better cooling channel design to remove those hot spots. And wattage problem is the same with the experimental trend. So if you want, you can do some design change and to see whether it can be improved. For example, if you improve, modify the melt temperature, like increase 5 degrees Celsius or reduce 5 degrees Celsius, maybe somehow the wattage can reduce a little bit. And we also provide the actual production of the black line and wattage tendency. So this also proves the software so far have a good accuracy. Okay. Okay. So any question? So that's what I would like to share with you today. And if you have any questions, I'm happy to answer.
Yeah. So I think it's very interesting when you talk about the phase separation, right? So what I'm getting is that because due of a shear phenomenon, the the result of the powders inside the solution separated because you'll basically have some pressure going on. So my question is that if the powder has a different particle distribution, will that phenomenon get mitigated or does it get worse? Or how do you put prediction and simulation kind of forecast?
Yeah.
Because I think the research group at USA, I know they do fiber, right? There's fiber orientation, but they're assuming they are all equally amount the same size. Right? So my question now comes into what happened if it's I'll keep it simple, just spherical, right? But there's a distribution going on. Do your simulation take into account the distribution or no? Not this one.
That's a very good question. Yeah. As you mentioned, right now we are also trying to improve or make it better for the this is the school, right? For example, if we improve we hope if we improve like a 60 weight percentage uniform, but through the school, sometimes we should simulate the mode. For this region, actually, we already have some initial like a profile. Maybe somehow already have some non-homogeneous or maybe a profile. Especially for fiber, it's very
Difficult.
Yeah. So I should say this is a good question, but we are still working on that. So that's also the why we need most of you doing the research. Right now we are just like we can already do something, but we always have more research.
So just out of curious when you talk about the phase separation, so when you have is it high shear, meaning that you have more concentrated powder inside a solution, and low shear you have less concentration, right?
Opposite.
The opposite, right? So is it possible with the solution if you add some surfactants or something like that, will that improve, or is just this is more of a mechanical phenomenon?
I'm not sure.
So if I ask,
Maybe.
yeah. So does this phenomenon only happen in a very tight, like a screw, like a barrel, or does this kind of phenomenon also happen as long as I give a shear, you will see that phase separation? Because I'm just curious because I saw the phase separation in your slide. It is usually in a very tight like nozzle, right?
Yeah.
So
But actually, have that everywhere.
so
Like every position, you have a shear rate profile.
yeah.
Keep going.
So as long as there's a shear thing going on, there will be a phase separation that separate the powder and the solution.
Yeah.
Okay.
So this is like a accumulated somehow you have some distribution, and once it goes into the some region, it getting worse.
Right. So the powder basically some part they concentrate, some part they kind of more disperse. Right?
Yeah. Right.
So I was just wondering, for the binder side, is there any people they want to put some surfactants or senpai,
I guess, yeah.
anti-sediment to avoid these kind of mechanical phenomena?
I guess some
Like
of them
that.
are doing that.
Okay. Yeah. But this is this currently still an issue?
I'm not sure. I focus more on the simulation. But I believe if you can increase the binder and the addition force,
Right.
it can somehow reduce like 10%.
Okay.
I guess.
So another question is because since I'm doing MIM, the metal and powder, I think it's safe to say that we never have the same size. There's always a distribution. And not only, sometimes these particles might not be spherical. It might be
that's another
so it's more difficult.
Yeah.
Another thing is for your constitutive equation, do your constitutive equations take in consider if it's today's metal or ceramic or powder? Because these powders, their surface energy is very completely different from carbon fibers surface energy. I don't know if you know will that affect or
Yeah. So right now we only, so our equation is the same, but we always use the aspect and over the ratio, and here is like equal to 1, and for this shape maybe it would like 20 or to 140. But as you may assume, this is uniform initially.
right.
But maybe real case, some portion is combined with
Okay.
yeah.
So just a follow-up question is supposedly, like if it's all spherical, for your simulation, does it show the same when I do metal ceramic and metal spherical and ceramic spherical? Do the results show the same or different?
Oh, okay. Maybe result is a little bit different. Yeah. See, I believe since we are mixing the mixture combined with the metal or the ceramic,
Yeah.
that will give us different viscosity,
Right.
different purity.
Yeah.
So the flow behavior will change.
Yeah, so this is very interesting. Maybe we can talk a little bit later because, so the reason the viscosity is different, is it because of density? Or is it the surface energy or? Because they're all spherical, how would the viscosity be different? Is it because density or heavier? Or the surface energy because metal has
Yeah, that's a good question.
higher surface? So this got into, I'm very curious about your equation. Does it consider, all these phenomena?
Oh, by the way, so actually we also have like some idea. So for this material, we can take this as a black box. We don't know what is exactly how many percent or what is the binder wax or something. We just treat this as a black box and do some tests so we can have a average viscosity behavior.
Right.
And yeah, but if you want, like you mentioned, you may know what is the more detail, like a white box. You know exactly what fiber you are related to, so you can have a more control, more idea for that. Yeah.
Right. So yeah, I think it's definitely more interesting, in this field. Although stuff I just wanna, because in your slide you also show some MIM talks. So I just wanna make sure, currently for Modex video, they only predict, simulate like the green body, right? Do you guys also do simulation once they go through ground body and center body? Yeah.
Yeah, as you mentioned, we only do the green.
Just the green body when it flows in and solidify, right?
Yes.
Okay. So for the polymer side, for the binder, right? How do you? Because polymer by itself is already very difficult because it's a strain rate dependent. So how do you, what is these constant equations that, did you have your own constant equations or how did you?
Right now we are just doing from the pattern, the same with yeah. We don't have our special one.
Okay, I see. Yeah. No, it's definitely interesting. Like when we have metal, it's different, even more difficult, complicated.
Right.
Okay. Yeah, sure. Okay. Yeah, so do we have any question from the audience? No? Okay, if not, let's
Okay.
yeah, let's thank you, Professor Dr. Tom again for this presentation.